I had my instructions. Well, since it is now 4, today I'm excited to introduce Jessica Liu, who is an assistant professor of astronomy at the Institute for Astronomy at the University of Hawaii. Jessica earned her bachelor's down the street at MIT in 2000, and then obtained her PhD from UCLA, working with Andrea Ghez on star formation near the center of our galaxy. From there, she took a Millikan Fellowship to go to Caltech, and then further with an NSF Fellowship to Hawaii, where she joined the faculty last year. So Jessica's research is focused on star formation, which I think most of us got a taste for, or this lunch at the ITC lunch. And her particular interest is on how the galactic environment affects the stellar initial mass function. And to pursue that interest, she has become a world leader in adaptive optics observations of stars near the Galactic Center, of high precision long baseline astrometry, of integral field spectroscopy, and of photometry in extremely crowded star fields. So among her many activities, she is the co-chair of the 30-meter telescope International Science Development Team on the formation of stars and planets. And today, she will talk to us about star formation in extreme environments. So please, Jessica.
Thank you for the invitation. I'm very happy to travel very far to come, but I have to say the weather, you guys could have tuned a little better, especially coming from Hawaii. Many of the results I'll be presenting today are in collaboration with the UCLA Galactic Center group, many of whose names are listed down here below, and also Jay Anderson at Space Telescope with some of the HST astrometry I'll be presenting, and then my 2 students that I've been working with, the IfA, Matt Hosek and Ding Huang. All right, so this is just a picture, an artist's rendition, of what our Milky Way galaxy looks like. And I wanted to start with a little bit of context about where our knowledge of how stars form comes from. We live out, I'd say, in the suburbs of the galaxy, not quite the boonies, but about 2/3 of the way out, as you can see right there. And most of what we know about star formation comes from a very local volume around our own sun. This is a 500 parsec radius bubble, which includes Taurus and Orion, some of the best studied star-forming regions. And yet you can see this is not necessarily representative of star-forming conditions, or the conditions where star clusters form throughout the rest of the galaxy. In fact, towards the center, as you go in, you can see how much more dramatically extreme the conditions get. Certainly the stellar densities are higher. But there are many other properties that change as you go into the center of the galaxy. And so you might wonder, out here in our barely even a spiral arm, the local Orion arm, that's where we know most of what we know about star formation. How does it change when you go into these much more extreme conditions? And extrapolating even further, when we go to other galaxies, of course, are those conditions in the Galactic Center, for instance, comparable to other star-forming galaxies, much more rich in star-forming, higher star formation rate galaxies, and maybe even galaxies in the early universe. So that's the main motivation for why I'm interested in pushing our boundaries of where we study star formation out into these new and uncharted territories, I'd say. So in terms of what we study locally, just to give you a sense of scale, the Taurus molecular cloud has about 100 solar masses and stars, and it's 140 parsecs away. And this is just a picture. You can see how sparse it is. One star forming over here, let's see if I can get this to work, down here, for instance, has very little impact on the stars that will form up there. So a very low-density star-forming environment. Our prototypical high-mass star-forming environment that we study is Orion. Orion's about 2,000 solar masses, substantially bigger than Taurus, 410 parsecs away, and you can see there are about four OB stars, plus all their companions, in the center of Orion. This is our massive star-forming region that we study. And then we can compare that to star clusters like this. Here on the exact same spatial scale, this is Orion down here, 1,000 solar masses or so. Here is NGC 3603 in your lower left corner. That is a 10,000 solar mass cluster. And then R136 or 30 Doradus in the 30 Doradus region in the LMC, which is shown in the big picture here. Now we're talking thousands of OB stars. And the stellar densities are dramatically higher. and the extent of the cluster is larger, dynamical interactions should be quite extreme compared to something like Orion. So how is star formation different, if at all, in this region? These massive star clusters, there are very few of them in our own Milky Way, unfortunately, and they are quite distant. So that's why we haven't studied them in great detail so far. The clusters that I'll mostly be talking about today are Westerlin 1, the Arches, and the young nuclear cluster. And here's where they live in our Milky Way. Westerlin 1 is probably about 3 kiloparsecs away in a spiral arm, and then Arches is about 30 parsecs from the center of the galaxy, and then the young nuclear cluster is spot on right surrounding the supermassive black hole at the Galactic Center. All these clusters are young. That's why we're studying them in terms of star formation, and over 10,000 solar masses. Okay, so the main question is, do stars form the same way in different environments? And we can show the canonical picture of how we think stars form today. This is a requirement in all star formation talks, I think. Someone told me that once. So you have a molecular cloud that clumps up, you form individual clumps, and then rapidly the picture goes to a single star, and there's no more interactions in this paradigm between stars anymore. So the one clump collapses, you get a disk and a protostar and an envelope. Eventually the envelope dissipates, you have a disk and a jet, and eventually planets. That's all well and good. But in reality, the picture looks something much more like this. This is a simulation by Krumholtz, Klein, and McKee of a molecular cloud that collapses and produces stars. And you can see the stars are interacting, they're dynamic, they're flowing through very different environments, accreting material from their surroundings. Their accretion rates change dramatically with time. This is inherently a dynamic process, and I think it's hard, especially in these massive clusters, to separate star formation from cluster formation. We already know that the star formation process is impacted even in Orion. We see this. These are proplyds in Orion, low mass stars with disks around them and modest outflows that are being photoionized by massive OB stars, for instance, off in the distance, the trapezium stars. We see that these massive stars are influencing these low mass stars. We just don't know to what degree. Do they change the resulting mass of this star? Do they change the formation of planets around this star? Those are the things we would like to know. So ultimately, we'd like to investigate the outcome of the star formation process, which is the initial mass function. Here is one of our best initial mass function measurements today. This is in Orion, in work from De Rio et al. This shows the number of stars versus stellar mass on a log scale here. You can see the canonical salpeter slope at the high mass end, above about 0.3 solar masses, which is where the peak is, roughly speaking, in Orion. And then the low mass tail falls off here. And this seems to be roughly consistent with this two-part power law, although depending on what models you could use, you could fit a log normal distribution to this with a high mass, with a tail at the high mass end. So that's our best estimate for the IMF in Orion today. There was a nice summary paper by Nate Bastian and et al. In 2010 that looked at the IMF as a function of environment, but they had a very limited sample. Again, these are all clusters, for the most part, that are in the local volume. This is their IMF, and you can see at the high mass end, almost all of their slopes are identical, and certainly within the uncertainties, which can be quite large for some of these clusters, which are relatively low mass, all the slopes are identical. So if you ask a standard stellar astrophysicist whether the IMF is universal, they would say yes. There is, if you look carefully, the slopes at the low mass end show some differences. The error bars here, I can't even plot them, they're so large down at this low mass end. So we don't yet know whether the low mass end of the IMF is changing dramatically. There's also some indication that perhaps the peak of the distribution changes. As you can see, Taurus, for instance, peaks at a slightly different mass than Orion, some of the other clusters. So stellar astrophysicists believe the IMF is universal. But if you were to ask an extragalactic astrophysicist whether the IMF is local, they robustly say no, it is not. We expect it to change as we look back in cosmic history or at different types of galaxies. And in fact, there has been some work in the past few years. This has been quite a cottage industry. Some of it started by Van Dokkum and Conroy in 2010, where they've used spectra, whole galaxy spectra, and looked at particular spectral features to try and trace the number of dwarf main sequence stars and the number of slightly more massive giant stars, and look at the ratio as a constraint of the IMF. There's also been work on mass to light ratios, again, trying to constrain the IMF. And what they've been finding is in the most massive elliptical galaxies, you see that the IMF that they get, or these indexes, these spectral indices that they get, are not consistent with a salpeter initial mass function or a Krupa initial mass function, these that we commonly assume. In fact, most of their indices suggest that the IMF is in bottom heavy, more low mass stars than high mass stars. This is quite unusual in these very extreme, very dense environments because many basic theories of star formation would suggest that you would move towards a top-heavy IMF if you move towards anything in these galaxies. So this is quite a puzzle as to how you produce a bottom-heavy IMF in the most massive galaxies, especially if you believe the biggest galaxies are built from low-mass galaxies. They just add together. So how do you produce such differences in the IMF? And how do we see the same thing, that the IMF is universal locally? So we clearly need to expand our local volume. Our IMF measurements, we need to make them now in different regions, something that's a little more extreme than our Taurus and Orion and local neighborhood. And so that's what I've set out to do with these massive cluster samples, is to look at their initial mass functions. So conceptually, pretty straightforward, but there are many challenges observationally that has prevented this work from being done in the past. The clusters are distant. They're very extincted. They're right in the galactic plane. So we're talking about extinctions of between AV of 10 and 30 at times. They're very, very crowded, and you are confused between what's in the cluster and what is in the foreground and the background. Here's a picture of the Milky Way plane where many of these clusters live at optical light. You can see it's pretty hopeless. A lot of these clusters you can't even see in the optical at all. 1 out of every 10 billion photons makes it to Earth. We have to go into the infrared to do these studies in the first place. This is the infrared plane, and instead here we're talking about 1 out of 10 photons. Still a bit of a loss, but something we can handle. The high spatial resolution is essential. This is an HST infrared image of the Arches cluster at the Galactic Center. Even with HST resolution, we cannot distinguish individual stars in the center of the Arches cluster. I'll show you more on that in a moment. So we absolutely have to have high spatial resolution. Seeing limited images don't cut it for this kind of work. So that leaves us with 2 options for how to pursue this project. One is ground-based imaging and spectroscopy with adaptive optics. This gives us the diffraction limit back again. We remove all of that horrible turbulence in the Earth's atmosphere, or at least most of it, and get back these spectacular diffraction-limited images. Again, this is at the very core of the Arches cluster now, for instance. And here's that this HST image that I just showed you. You can see here this clump over here that turns out to be 4 or 5 stars is, very, very messy and hard to distinguish over here. And this is just the brightest stars. As you go down the luminosity function, the crowding just gets worse and worse. So you can see the advantages of AO. We do some work with HST as well, which I'll present today. But AO is really far and away the most superior thing that we can get in terms of resolution. Okay, this is just to hammer that point home. We cannot do this with seeing limited observations. This is the center of the galaxy with seeing limited observations, and here it is with adaptive optics at Keck. And just for reference, I'm going to be talking about the Galactic Center cluster. Most of the bluish-looking stars that you see in here are all part of the young nuclear cluster. Those are the young nuclear cluster members. Okay, so given these observational tools, we can dive right in and ask, what is the initial mass function in this young nuclear cluster at the center of the galaxy? This cluster, the young stars here, were originally identified via spectroscopy. Actually, there was some indication of some early observations of bracket gamma emission with just very low resolution photometry. But with spectroscopy, we rapidly discovered that many of these are Wolf-Rayet stars. These are evolved O and B stars. That puts them at ages between 4 and 8 megayears or so. Today, with our spectroscopic census, we know of at least 120 OB stars. That roughly scales to a cluster mass of about 10,000 solar masses. And it's all confined within a 1 parsec box right around the black hole. And the black hole is located right here. This picture, all the red X's on here are young stars, and this is a few years out of date, so there are many more being discovered now. We've done quite extensive dynamical studies and radial velocity studies of these stars, and we've measured their orbits and their motions in the sky. We know that the dynamical structure is quite interesting for the young stars. They seem to form a disk plus an isotropic population. The disk, about 30% of the young stars fall on this disk, and the disk has a very steep radial profile. Both of these suggest that these young stars really did form where we see them today, right around the black hole, probably in some kind of a gaseous disk or from the infall of a giant molecular cloud. The environment in this region, right around the black hole, is very extreme. It's about as extreme as we can get in our Milky Way galaxy, at least. It has very high temperatures. The gas densities to form stars have to be on order of 10 to the 10 particles per cubic centimeter to overcome the tidal shear from the black hole alone. The magnetic fields are most likely pretty high, and the incredible stellar density in here means that dynamical interactions are frequent. So we conducted a spectroscopic survey of this region to identify all the young stars and really push down to try and measure the mass function. We did this along this plane of the disk, extending out from Sagittarius star radially. All the blue stars here are marked, all the blue circles are marking the positions of young stars that we know about. You can see they're in the minority. Only about 30% of the stars in this region are young stars. And so it's a very tedious and painful process to identify each and every one. This is adaptive optics integral field unit spectroscopy. Each one of these boxes is one field of view, and you can see we had to stitch together a lot of data to do this. This took a while. But in the end, we were rather surprised to find that the K-band luminosity function turns over, but it turns over in a way, it rises. These are the highest mass stars, maybe 40 solar mass stars. And then it rises, and then it turns over, but at fairly high masses. But once you correct for completeness, it continues to rise. So, you know, it's kind of as we would expect, but we really set out to do some detailed modeling of what the initial mass function was in this regime. There had been some previous results that suggested the IMF looked like this blue curve here and turned over at roughly 30 solar masses. So instantly when we made this measurement, we knew that we weren't going to get a top-heavy IMF where the IMF just cut off at 30 solar masses, which had been in the literature for a little while. So we set out to model the star cluster. We start with an initial mass function. That gives us a list of stars with masses. And then we push this through stellar evolution models. We just assume solar metallicity at the Galactic Center, which is actually a pretty good approximation based on some high-resolution spectra. That gives us properties, intrinsic properties of the star, like luminosities, effective temperatures, and gravities, and the number of Wolf-Rayet stars we might expect at a given age. We push those through atmosphere models, given some distance, which we know, and some extinction, which we know but can also fit. And that gives us an observed K-band luminosity function, and that's what we're comparing with our observations. This is, schematically, it's a pretty straightforward process, but there's a lot that goes into this, as it turns out, and as I talked about today at lunch, but I'll just summarize quickly. We had to stitch together a bunch of different evolution and atmosphere models. There's no one set of models that spans the entire mass range, all the way down from, well, especially for pre-main sequence stars, from 0.1 solar masses to 150 solar masses. Now, we're only detecting sort of 8 solar masses and higher in the Galactic Center, so maybe that's not such a problem, but for much of our work, this mechanism that we wanted to build a tool that was useful for many other star clusters, as you'll see in a moment. The atmosphere models are also, we had to stitch together quite a few to span a full temperature range. Okay, we also had to deal with multiples. This was something unusual we didn't expect. When we started looking at luminosity functions, predicted luminosity functions, they all cut off at a magnitude of about 11.5, and yet we saw massive stars, OB, almost main sequence stars, right around 10th magnitude. So we were seeing things that were too bright. And on hindsight, this was obvious. It was their binary systems, almost for sure. So we had to include multiplicity within our models. So we have a whole lot of model parameters, but in the end, what we're mainly interested in is the slope of the initial mass function. All of this was modeled in a Bayesian inference method where we modeled 10,000 clusters and compared them with our observations, exploring all of this parameter space. And as a result, what we get for the young nuclear cluster is an age of about 4 million years, not quite 10,000 solar masses, at least in terms of within our field of view, but if you project outwards to cover the complete azimuthal coverage, which we didn't have in our spectra, you get something around 20,000 solar masses. And the IMF slope that we get is around 1.7, where a salpeter slope is 2.35. And we can rule out a salpeter slope at something like 3.3 sigma. We can also rule out a very, very top-heavy slope, which some previous results had claimed at very high significance as well. So the bottom line is in the Galactic Center, at least, it looks like we have an IMF slope that is significantly different from the salpeter model. We don't detect enough of these low-mass stars down in this range to match a salpeter model. And the problem with the Galactic Center cluster is we're only probing down to 8 solar masses. So we can say that it's not salpeter, 8 solar masses and above. Unfortunately, the most massive star in Orion is about 8 solar masses. So there's no overlap between the two clusters. That's quite unfortunate. So yes, there's something going a little bit different in terms of the star formation process in the young nuclear cluster, but maybe that's just the same everywhere. Maybe it would be the same if we had a very massive cluster locally as well. We didn't know. In the Galactic Center, we're completely limited by this need to identify all the young stars with spectroscopy, and that really limits the mass sensitivity. But other clusters, we have a lot more potential for more complete studies going down to lower masses. So here, for instance, is the Westerland 1 cluster. You can see the potential here. It's very easy, well, at least on first pass, to look at this cluster and say, these are cluster stars. I see them. These are all the members. But if I were to ask you whether this star right here is a cluster member or not, you'd be hard-pressed to tell me whether it's a cluster member just from images or photometry alone. Mostly in past studies, the way that membership has been determined for these clusters is you take an image of the Westerland one in this case, and you take an off-cluster control image that's a degree away, far enough away that you don't think you have any cluster members anymore. And then you construct color magnitude diagrams for both and do some kind of statistical correction for this color magnitude diagram, subtracting off all of these off-cluster stars. So you get rid of all the background and you're just left with, at least statistically, a cluster sample. The problem is for these young clusters deeply embedded in the galactic plane, there's gas in between us and them. And that gas produces extinction. And that gas is clumpy, highly clumpy. So here's a massive cluster, for instance. You can see in this cluster alone, in this infrared image, you can see the difference in extinction just across the face of these two parts of one cluster. This is a little double cluster. You can see even by eye, this changes in extinction going across here. So you have to be extremely careful about picking your off-cluster field to match the extinction values exactly. And that's very challenging to do. Instead, we can employ a technique that's been widely used in the globular cluster community for quite some time, which is proper motions. So here is a picture of the motions in the X and Y on the plane of the sky of many stars towards a globular cluster. And you can see all the globular cluster stars cluster together in proper motion space as well as space. Projected on the sky. And so you can separate out all the contaminating field stars from the cluster. Here's the resulting color magnitude diagram for everything, and then what a beautifully clean sequence you get as a result after proper motion membership selection. And then here's your field population. So this is great. This is exactly what we wanted to do. Unfortunately, all of this is done with HST in the optical, so not really suitable for these young clusters. So we had to move into the infrared, and globulars are flying around at much higher velocities around the galaxy. So they have a good separation between the background contaminating stuff, or foreground stars, and the cluster itself. The clusters we're interested in are right in the galactic plane, moving with everything else. So you really have to be careful and have very high precision astrometry to separate them out. We started with the Arches cluster because it's in the Galactic Center, and everything in the Galactic Center is moving a little bit quicker than, say, in the disk of the Milky Way. So the Arches cluster, we started a program with adaptive optics at Keck to measure the proper motion of the arches, and eventually with the hope of measuring the initial mass function. This is just an HST image to show you the Arches cluster, and here's where it is relative to the black hole. Black hole's down here, and the Arches is about 30 parsecs away. When we started our adaptive optics program, we had just been doing AO astrometry on the Galactic Center and just started developing these very high precision techniques. And so ultimately what we were getting is about 0.1 or 0.15 milli-arcsecond astrometric precisions. This is out of our adaptive optics data, which has typically about 60 milli-arcsecond resolution. So that was plenty good enough, we thought, to do the arches. And in fact, our latest results on the Arches cluster from Clarkson 2012 shows very clean separation between the Arches cluster and the surrounding background and foreground stars, so we can easily pick out the cluster members. Our proper motions were were good enough, in fact, to find a bunch of cluster members that we never would have found in any other way. In this work by Andreas Stolte et al. And all of us, we found this population of infrared excess sources in the Arches cluster. They're all proper motion members, and yet they have very different colors, and you would never even, if you made just simple color cuts, you would never include these as part of the cluster membership. And yet here they are, and naturally they're disk sources. They're A and B stars with disks still around them at the Arches age. This result allowed us to measure a disk fraction in the Arches of only 6%, which is a very low value compared to something like Orion or other similarly massed clusters, but is in line with massive clusters. So it looks like most massive clusters show lower disk fractions at a given age. Our astrometry for the Arches was good enough that we've gotten a dynamical mass measurement for the Arches. We can measure the internal velocity dispersion of the cluster, as plotted here. This is divided up into radial and tangential. And then if you model that, you can get the enclosed mass down here for the cluster. So the enclosed mass at a radius of about 0.4 parsecs is 10 to the 4 solar masses. The beauty of getting a dynamical mass in this way is that you can compare it to the photometric mass that we get. So if you look at the photometric mass, we're measuring down to 5 solar masses. We can project that down using some IMF and say, what's the dynamical mass you would expect? And that's what's shown here. This is the enclosed mass that you would predict for different types of initial mass functions. And there's two things that we change about the initial mass function. The slope of the IMF is trailing along here. Sorry for the change. Now saltpeter is 1.35 here. And then the other thing we're changing that's moving up and down is the low mass cutoff of the IMF. So if you say you only allow stars that go down to 1 solar mass, you get this box here. This is half a solar mass. And then as you go up to a normal 0.3 solar mass, low mass cutoff for the IMF, you get up to this point up here. So you can see that our measurement is in blue down here. This is what a normal IMF would be. This is normal-ish if you stopped at a solar mass. That's not normal locally, but maybe it's got the same slope at least. And then here is the slope range for that young nuclear cluster. So in fact, what we see for our dynamical mass measurement for the Arches cluster is that we have to have something peculiar about the IMF there as well. Either the slope has to be flatter, or the IMF can look normal at the high mass end but needs to stop, and low mass stars aren't really formed in the Arches. So the viable options are either a bottom light IMF or a top heavy IMF. Okay, so unfortunately, adaptive optics suffers from one, at least historically, suffers from one downside, which is the fields of view are incredibly small. This is that HST image of the Arches. This is not even the whole HST with C3IR field of view. And this is our typical adaptive optics in the green box field of view. It's about 10 arc seconds. So that's great for the Arches. We can get the core of the Arches cluster very well. But if you wanted to measure the entire Arches, it would be incredibly hard to stitch together, especially if you want precise astrometry. Mosaicing really kills you in terms of astrometry. So instead, we started an HST program. Unfortunately, in the cluster center, HST is not going to cut it, but AO will. But on the outskirts, you can see it starts to be sparse enough that HST actually can make some headway. We can still resolve the stars. With C3IR on HST, we can get about a milli-arc-second astrometry. It's at reduced resolution, but it gives us that astrometry over a 2 arc-minute field of view. And the half light radius of the Arches is predicted to be somewhere between here, the half mass radius, between here and that 2 arc-minute field of view. In fact, we don't know what the half mass radius of the Arches is. And that's because the Arches has been, we don't know its orbit, but it's been probably almost once around the galaxy. So it's had a huge amount of time to be tidally stripped and to expand or contract, whatever clusters may do in this potential. If it's on an eccentric orbit, it might be stripped down to very small radii. If it's on a more circular orbit, it might have a larger tidal radius still. So on our HST data set, we now have 2 years, 3 measurements spread over 2 years. And you can see from our astrometry here, this is again a vector point diagram for the proper motions, the motion on the sky in one direction and the other. You can see we can pull out the cluster members quite well. And then here's all the contaminating field population. If you're keen on this, the reason the field population is not symmetric is simply because all the foreground stars are rotating in the disk of the Milky Way. So it's just elongated along that direction. Here's our resulting HST color magnitude diagram before membership selection. You can see lots and lots of interesting structures. You could pull out the Arches cluster. Anybody? Not really. It's extremely challenging. This is a foreground sequence. This is a foreground sequence. The Arches cluster is somewhere in here. This is the red clump that's just showing the extreme amounts of variations in reddening in the galactic bulge. So going from AV of about 20 to AV of about 45 down here. So that has nothing to do with the Arches. After membership selection, this is the resulting color magnitude diagram. Nowhere as nice and clean as those globular clusters, but that's for one simple reason. We have this huge amount of differential reddening here that we have to get rid of. So we construct a reddening map here and apply it. All these reddening is actually constructed from this very nice sequence of red clump stars. So we use that to make a measurement. Yeah.
You're showing colors. Are those HST bands?
Yeah, these are HST bands, and if you don't know how to read them, that's 1.27 microns and 1.53 microns. Yeah, sorry about that. Okay, so this is the red clump. You can see the red clump we know pretty well. It has basically one luminosity, so we can just measure the reddening along here and make a map of it. And so once you map the reddening and apply that, here's the cluster before, and here's the cluster after. And so now we're starting to see something nice and clean. A few contaminating field stars that just happen to have the same motion as the arches. As we continue our astrometry, we will get better and better at cleaning out these sources with better astrometric errors. So in terms of sensitivity, our previous AO data was getting it down to about 2 or 3 solar masses, just right in the core. With this HST data, we're also able to get down to 2 solar masses, now simply because we're not in the core. It's too crowded in the core. But in the outskirts, we can get down to 2 solar masses. And so we're in the process of deriving the initial mass function down to 2 solar masses with this. This is pretty much hot off the presses from my student, Matt Hosek. Here's a picture of all those cluster members that we had identified. You can see the contamination is relatively small, less than 10%, probably more like 2% of the population are not cluster members, most likely. And on the red side here, these probably a lot of them probably are cluster members. They're these stars with disks, as we said before. Maybe not all of them, but most of them. Okay, here are the cluster members just plotted on the plane of the sky and their motions. You can see how far out they go. We have cluster members almost over the entire field of view. And so what we're planning on doing is use this to model the tidal radius of the cluster, and that gives us a constraint on the orbit, where it's been, its history. And we need all of that because what we actually measure is not the initial mass function in the arches, it's the present day mass function. And we have to back out what the initial mass function was. And because it's been around the galaxy once, it's lost a lot of stars, and it's probably lost stars proportional to mass somehow. So we have to make a correction for that. Okay, so I just wanted to show this because I think astrometry over a large field of view allows us to test the IMF, the radius of the cluster, the tidal stripping, the cluster structure. It gives us a more complete picture if we study the entire cluster, and that's very important for something like the arches in this kind of environment. So that's a work in progress, but so far what we have is the arches is certainly probably bottom light above 5 to 10 solar masses. Maybe it's a top heavy, same as the young nuclear cluster, but any way you look at it, it's not a normal IMF. It's been limited, our studies of the arches have been limited by our imaging sensitivity. So we can do everything with imaging, but we're still stuck around 2 solar masses because it's so distant and so reddened. And also, it's still in the Galactic Center environment. We know in the Galactic Center, molecular clouds are quite different from molecular clouds in the Milky Way disk. They have higher turbulence, higher densities and pressures and temperatures. That's a different initial condition than the disk. So if we wanted to compare to the disk, I rapidly ran into the question of, well, what's the IMF in disk massive clusters? And there were no measurements, or there were a few. So that's where Westerlin 1 comes in. Do these IMF variations hold in the galactic disk? So we see something strange in the Galactic Center, but is it just a function of the Galactic Center, or is it just because it's a massive cluster? Which one is the most important factor? So to do the astrometry experiment that I just showed in the Milky Way disk is even more challenging. These clusters are moving at the same speed as everything else in the same spiral arm. You need incredible precisions, and the question was whether we could even do it. We had to think carefully about which clusters to look at. If you put all the massive young clusters on a face-down view of the Milky Way and put us over here, if you look towards clusters like Westerlin 2 or NGC 3603, there will be very little differential proper motion because you're looking right down a spiral arm and everything is moving mostly radially away from us or towards us. So those are not good clusters for looking at proper motions. Let's see. Instead, some of the good clusters are the ones towards the center or where the spiral arms are bunching up over on this far side. And then, for instance, Westerlin 1, you can see its proper motion of stars as a function of distance along that sight line. Here's foreground stars up here, there's the cluster, and here's background stars. So if we measure proper motions in the direction of Westerlin 1, we had a hope of being able to at least get rid of all the background stars and a lot of the foreground stars if we could just measure the proper motion there. So that's what we set out to do. Again, this was a program that the data was all in the HST archive. Here's a picture of the HST image of Westerlin 1. You can see the cluster is closer, it's larger. It's about 5 million years old, but it's also more massive, 10,000 solar masses. So a very interesting cluster to study. Here's our proper motion results for this cluster. You can see, this is zoomed in now, but you can see the cluster quite cleanly from the background field population here, background, foreground, and field population. This is a combination of HST infrared and optical, because that was what was in the archive. The first epoch was optical. It's highly extincted still, AV of about 15, so the optical data is not incredibly deep. Here's the color magnitude diagram. This is 814 nanometers and then 1.25 microns. That's just the HST filters here. Again, you can see lots of interesting stuff in this data, all these interesting sequences, which I think is a project in and of itself, but I'm not going to talk about that. Westerlin 1 is buried in here. So that's before membership selection, and here's after membership selection. So again, we have a nice clean sequence. We're still working on the differential reddening for this cluster, but you can see we can get down to a solar mass in this cluster, and that's with an optical limited data set. Again, this is just showing the membership. We actually do formal membership probabilities, identifying cluster members and contaminating field stars. And then we do the same exact process that we've done on the Galactic Center, which is to model the young cluster. Now we're just predicting multiple magnitudes. We don't have just a K-band luminosity function. We have full CMDs, and so we're doing a full analysis to compare with our observations. What we get is the following. Here are our, we have several different bands of data, and here's our color magnitude diagrams with all the points from proper motion membership selection on Westerland 1. And in color lines are a range of different isochrones that could fit the cluster. Each one has a different age. Here's the logarithm of the age. And then each one has a slightly different extinction value and a different distance. Turns out the distance is uncertain by a factor of 2 towards Westerland 1, which is a bit unfortunate. So there are a lot of different models that could fit, and we have to pick out which one we think is correct. More importantly, the models don't even fit the data very well. So you can see these are two different color magnitude diagrams. This is infrared only, and this is optical and infrared. And I can fit the data reasonably well in the infrared, but not in the optical. I can't fit the main sequence. I can change models and fit the main sequence, but then not the pre-main sequence. So something is wrong in the models themselves that's not able to reproduce what we're observing in this cluster. Here's another view just showing the color plot. And you can see the main sequence here lying right on one of the models, or shifted, and then the pre-main sequence is off by 0.15 magnitudes. HST photometry is good to 1 or 2%, and we can't match it because the models are uncertain by the 0.15 magnitudes down here on the pre-main sequence. This is a real limitation to deriving an initial mass function because of the following. If you model a synthetic cluster and you use that same model with all the same input parameters to try and recover the IMF, you can do a fine job. Here we synthesized a cluster with a slope of minus 2.7, just a very bottom-heavy one, a steep one, and then we can get back out minus 2.65, and within uncertainties we agree with the input value. If instead we change the model slightly, so such that it still fits the color magnitude diagram just fine, but has a slightly different age and distance, or a slightly different extinction and distance. Instead, you get these wild blue points that are moving all over the place with dips and wiggles, and the resulting fit is very bad, with a slope of minus 3.6, but seemingly very precise with an uncertainty of 0.1. So it's incredibly important to get the models correct to be able to recover the correct initial mass function. And that's really what's limiting us today, is we need to improve the models, figure out a way to improve the models before we can have a hope of recovering the initial mass function. But I'll show it to you anyways. Here are two different possible model values and the resulting IMFs that we get out. And you can see already they look fearfully awful because they have these dips and wiggles, which seems to indicate that we're probably using the wrong models, or the models themselves are not correct. We're not able to get something that looks smooth in terms of a mass function. This one's a little bit smoother, but it turns over and has this flat bottom. This one has these dips and wiggles here. And you can see these parameters are wildly different. Factor of 2 in distance and factor of 3 in age. And yet they both fit the color magnitude diagrams. So we're also in the process of getting spectroscopy for the high mass stars, which are bright enough to get spectroscopy of. And we can hope to constrain some of these parameters in that way as well. Okay, so also we'd like to push down on the mass function here, because if we had a good constraint, if we had better information here, you can see in the infrared, for instance, it's pretty vertical, and then you have the pre-main sequence turn off. But there's actually a lot of structure down here, and if we can measure this structure really well, we could actually start to constrain the models a little bit better. We have a program now getting infrared-only second and third epoch astrometry on this cluster. And you can see our photometry and hopefully our astrometry too will get us down to about 0.1 solar masses. So we'll be able to measure the IMF in Westerland 1 very soon. We'll get the last epoch next summer. Between 50, well, the stars go up to 60 solar masses all the way down to about 0.1 solar masses in this cluster. And you can see there's thousands of stars here, so we have a very precise measurement of the IMF, hopefully. Okay, so in context, the IMF for Westerland 1 is to be determined. We're stuck on the modeling stage at this point, but it's down to 1 solar mass in terms of the data, and soon we'll get down to 0.1 solar masses. So that's coming shortly. So a lot of the data I've presented to you was HST astrometry, and some of it was AO. So I just thought I'd go a little bit into some of the other work that I do. So high precision astrometry in crowded fields, I would say, is really, really helped by adaptive optics measurements, as you can see here. And we'd like to do a better job at AO than we can today. And there's a lot of different ways that we're pushing forward on this technology to try and improve our scientific capabilities and really take advantage of that spatial resolution that we can get out. One particular project that we're working on is a next generation adaptive optics project at Keck. This project will boost our strels by an enormous factor. In particular, it'll allow us to get very high strels at shorter wavelengths, J, H, and K. So now we'll be able to do complete color magnitude diagram analysis with very precise astrometry for a lot of these clusters, the cores of these clusters in particular, like the arches and quintuplet, where things are really crowded. This is so good that we may be even able to push to other clusters and other galaxies, nearby galaxies, and resolve individual stars there. You can see what a dramatic difference this makes in terms of sensitivity in crowded regimes. Here's some simulation work that we did at the UCLA Keck Galactic Center group. Here is an image of right around the supermassive black hole, just showing you what the stars look like when we take an image. Here's what it will look like with Keck Next Generation AO with a much, much higher strel or much higher image quality. You can see how many more stars we can detect. Here's a corresponding luminosity function or a completeness curve. How complete are we? So right now we can get down to about 19th or 20th magnitude in imaging. That corresponds to about 2 solar masses in the Galactic Center. Once we have NGAO, all we're changing is the AO system and making a better quality AO system. Then we can get down to about 0.25 solar masses, pushing down just a couple of magnitudes. So that will be a dramatic improvement in our ability to measure the IMF. Spectroscopy-wise, remember I said our earlier measurements, we were limited to about 10 solar masses. With the new system, we'll be able to get spectra down to about 3.5 solar masses. The other thing we're pushing on in terms of AO is we'd like to expand beyond this boundary of this 10 arcsecond field of view, and we're already doing this. At Gemini, there's a wide field adaptive optics system called the GEMS, the multi-conjugate AO system. This adaptive optics system uses many stars in the sky to measure the turbulence in the atmosphere, and then you have these very fast deformable mirrors, and you have multiple of them. Classical AO, you only have 1. GEMS has 3. And with those multiple deformable mirrors, you can model the turbulence at different layers, and that allows you to apply AO corrections over a much larger field of view. In fact, classical AO systems, the correction is typically limited to something about the size of this star. The wide field AO system at Gemini can give you something about the size of this constellation here, about 2 arc-minute corrected field of view. We've got some preliminary data from GEMS over the past year from their commissioning, and now they're into science observations. This is a cluster globular, NGC 1815. This is a 2 arc-minute field of view, and you can see the resolutions are 80 to 90 milliarcseconds. This is a factor of 2 better than HST at infrared wavelengths. So it's not quite diffraction limited, but they're still working on the system. And so with this spatial resolution, we could hope to get very precise astrometry. And so I've been working on the astrometric characterization for the system. In terms of astrometric precision, it looked great. The astrometric precision you can see for sparse fields, in the middle it gets down to about 0.2 milliarcseconds and then grows a little bit because you just run out of reference stars. For crowded fields where you can apply some high order transformations, you can get 0.2 milliarcsecond precision everywhere. So that's very comparable to Keck, but now over a 2 arc-minute field of view. Just to remind you, here's that single conjugate AO, normal AO, I'd say classical AO, their field of view limits, 5 to 10 arcseconds. Unfortunately, GEMS is turning out not to be such a great astrometry machine. It has night-to-night fluctuations. The instrument is a cast-mounted instrument, so it's flying around the back of the telescope. And gravity vector changes are introducing systematic astrometric shifts. You're moving your beam through the optics in different ways. That introduces time variable distortion. So sparse field cases, we're only getting to 2 milliarsecond astrometric precision. This is hopeless for all of our cluster cases. Even in crowded fields, we're getting down to 0.6. That's a factor of 4 worse than what we can get with Keck AO. So that's an unfortunate byproduct, but still, I think there is some work we can do, particularly for the closer clusters, which are less crowded, that have larger motions. We could still hope to do some interesting work with this system as well. Okay, so with all of these AO experiments, our ultimate goal is really to get astrometry of a young cluster, not in just the core. We want the whole thing, because in this star formation picture, you're looking at an entire molecular cloud. And you can see all of the filamentary structure. We would love to be able to measure this in young clusters, very young clusters. The youngest clusters, the million-year-old clusters, we're not going to see very far away. They're behind too much extinction just from the molecular cloud itself. We're stuck with the closer ones. The closer they are, the bigger they are on the sky. So we need even bigger than the GEM system, AO fields of view. And we're working on that as well. We have a ground layer AO system. This is the same thing as what I showed you before, multiple guide stars. But now you still have one deformal mirror, but you say, I'm going to sacrifice resolution. I'm only going to correct the turbulence that's down low. And if I sacrifice that resolution by only correcting the low-level turbulence, I can get a really big field of view. And what we're setting out to do is determine what that really big field means. We don't actually know what the limits are on this type of AO. So we have a project started at UH on one of the small telescopes on Mauna Kea. The project is called IMACA, and we will demonstrate AO over 7 to 21 arc-minute fields of view. So this is a big step up from what we're talking about before. And I think this is important in the era of something like JWST, which will have a 2 or 4 arc-minute field of view. These kinds of fields are substantially bigger than JWST and would allow us to study young star clusters nearby with good astrometry, with exquisite detail, especially if we can do repeated measurements over many, many years with a stable system. So the science cameras here are between 7 and 17 arc minutes. The guide star selection is within 24 arc minutes. These are whopping big fields of view for anybody who does AO. I don't even know what kind of astrometry we're going to get. We don't know what astrometry, precision astrometry will look like in these large fields of view because we actually honestly don't know what the turbulence is doing on these kinds of scales in the Earth's atmosphere. In the end, though, we hope, based on our modeling, the resolution of the system should be at least a factor of 2 improvement over seeing. So this is showing you what kind of probability or how often we will get seeing resolution of this level. So about 50% of the time we should be around 0.3 arc seconds seeing, so 300 milliarc seconds. So that's a factor of 5 worse than Keck, for instance. We should expect a factor of 5 worse astrometry. But at the same time, we can do this for clusters that are much closer and bigger on the plane of the sky than we ever could with Keck AO or even HST and JWST. So just to conclude and review, let's see if that goes. Oh, yeah, sorry. The Galactic Center, we've measured a saltpeter, that should be a non-saltpeter IMF, non-saltpeter IMF down to 8 to 10 solar masses, entirely limited by spectroscopy. It's slightly top-heavy. The arches is either top-heavy or more likely bottom-light based on some recent photometry that suggests it looks like it's saltpeter at the high mass end and then somewhere it breaks. That's also limited by our imaging sensitivity. And for Westerland 1, we're measuring the initial mass function now. We're really running into limitations with the models. And we would love to have a set of high-quality models that range from 0.1 to 150 solar masses that we can start playing and tweaking with. And then lastly, all of this work is helped by having wide field of view, high spatial resolution in the infrared. And AO on the ground is certainly one way to do that, and we're making headway on trying to improve AO fields of view to tackle this kind of science. But HST programs with WIFC3IR and eventually JWST, if JWST produces good astrometry, which is a big if, given that the primary is going like this all the time. If JWST produces good astrometry, this will be an excellent science case for JWST astrometry as well. The ultimate goal is to measure this IMF in as wide a range of environments as we can. A little bit in the distant future, for things like TMT and GMT, we can start to play this game not just in our galaxy, but in our nearest neighbor galaxies, including in superstar clusters. In the nearest superstar clusters, we will be able to resolve individual stars in those clusters and extrapolate or extend our IMF measurements into even these more extreme environments. I'll stop there. Thanks.
Thank you, Jessica. That's really neat. So, questions? Please, Trevor.
Here's what the limiting factor is now with the HST astrometry. Is it distortion? And if so, does the new spatial scanning data help you get better handling distortion?
So, prior to 3 weeks ago, our limiting factor was PSF variations across the field of view that weren't characterized. This is in WIFC3IR in particular. We've just fixed that. Jay and I got together and we've now put that in, and that's improved the astrometry at the edges of the field of view by a factor of 2 or more. Now the limiting factor is probably distortion. But spatial scanning doesn't help for crowded field cases. You can't scan and recover
I
stars.
meant the fact that they have to know the distortion extremely well, and so you get a really precise distortion map out of the spatial scan data.
Yeah. Potentially. Nobody's done it yet. They're working on it. But most of the scanning is done with the UV optical cameras, right? Not the infrared cameras. So if somebody were to do it with the infrared cameras, that would be fantastic.
Please, Alyssa.
Is there any chance that low mass stars have been ejected from the arches and are outside your field of view?
Yes. In fact, the tidal radius, we would expect that the tidal radius might be a function of mass a little bit, and that mostly low mass stars have been lost over high mass stars. And so what we hope to do is measure the structure as a function of mass and try and capture where they've all gone. Ultimately, we also hope to get the tidal streams, and we can look at the contents of the tidal streams versus the cluster core and put constraints that way. That should all come out of this HST program. Yeah. The same is true for Westerlin 1. In fact, we see not even just low mass ejected stars, but high mass. There's a neutron star, a magnetar, which is a little bit offset. It's probably been ejected from the cluster. So as soon as you talk about binaries, the high multiplicity fraction of massive stars, those things can eject all over the place as well.
John.
You said as you can go to these wider fields of view, and it seemed like you were implying that your astrometric precision was only limited by the widths of your PSFs. But if you went to a wider field of view, wouldn't you have more reference stars and to do a higher precision astrometry?
So it depends if you're talking about space or ground. So on the ground, we're not actually, we like to try as best we can to get to the limit of the resolution, but the biggest source of astrometric error is the atmosphere itself. The wider something is separated, the more astrometric jitter the atmosphere introduces. So as you go to a bigger field of view, you have to beat down this differential tilt jitter introduced by the atmosphere. For space, more reference stars is always better. Bigger field of view is better. But sensitivity is good too. So if your distortion solution is not perfect, you want reference stars that are close to your object. So go down until you can see galaxies, for instance.
Please.
What are the changes, the instrumental changes that get you from KKO to the next generation?
We're going to, right now, KKO has one laser that shines up to the middle as our reference star for measuring the turbulence. The new system will have, I think it's 5 or 7 lasers. They're still working on it. With those lasers, you can model the 3D column of turbulence that you're observing through, and you can model where the turbulence is at different layers. And then, depending on where you're looking, you can then apply different corrections so that your field of view, your field of view will be the same for NGAO. It won't expand the field of view, but it'll allow you to model all dimensions, all where the turbulence is, and that gives you a very, very high correction on axis. Also, a deformable mirror is has many more actuators, many more degrees of freedom than the current system.
Please.
Do you think that the top-heavy IMF that you found is an effect of the extreme environment versus stars form for dynamical evolution?
So for the young nuclear cluster, my guess is not dynamical evolution, simply because where do the stars go? There's nothing that can preferentially get rid of. Well, that's not 100% true. Not at the degree that we're seeing at this young of an age. You can't eject that many moderate mass stars relative to the high mass stars. There just hasn't been enough time for that cluster to process dynamically. You will get some slight mass segregation, which we do worry about, but it should be slight unless it's primordial. We have no idea what a molecular cloud falling into a black hole, turning into stars really looks like. There's lots of simulations, but they can run the gamut all over the place. And depending on exactly how you tune the cooling time, for instance, you can get no stars or everything turns into stars at 100% efficiency. So it's a really big uncertainty in terms of what the gas does. For the other clusters, I would say that for the arches, for instance, I'm guessing it's initial conditions of the molecular cloud, not so much dynamical evolution, but we're still investigating. Until we get the tidal radius measurement for sure, we won't know.
For the Galactic Center, shouldn't the tidal shear actually select out against high mass stars? Should you actually find, I'm surprised why you find the opposite result to what should be expected.
So the tidal shear will shear out any low density clumps. It will just shear them out and they'll never be able to form stars. So the only clumps that can survive are the extremely high density, high mass, presumably high mass clumps.
How do they get there? How do they get large to begin with?
You have to dump a bunch of mass in at one time. So most likely what happened is a giant molecular cloud fell in, or collision of two clouds nearby. We actually see a molecular ring that's got about 10,000 solar masses out just a little ways, about a parsec away from the black hole. And there's another giant molecular cloud that's coming in right now and intersecting. And so we think that this is probably a pretty common occurrence for these big streams of molecular material to plunge in quite rapidly. Once it disrupts this ring, everything's just going to drop down. And at that point, you have a very rapid infall of mass, and then you build up a disk very quickly with a lot of mass that can overcome the tidal shear and collapse.
Any more questions? Otherwise, let's thank Jessica again.